Hi, in this video we will talk about Sargan. So in this code, Sargan instance is created here. We have to go here. To open the code, we have to press Ctrl and we have to hover the mouse on this line. So it will show the underline and blue text. Then we have to click it. So it will bring us to the code of Sargan, that is stacked attention residual GAN. So this is the constructor. Init is a constructor, so automatically it will be called whenever this class is invoked. So what it does, first it is setting channel is equal to 3. Say whenever we use a class, we have to use self dot to access any variable. So channel is our variable, but as it is a variable of the class, we have to use self dot channels. So we have a 3 channel, then we are initializing the immune space shape. So that also we know that it is 224 by 224 by 3. Right? So 3 is coming from self dot channel that we have already set it here. So if channel is 1, we can make it 1, and this would be 2 by 224 by 224 by 1. But in our case, it is a color image. So there are 3 channels. Then image shape variable also we are setting it to the same parameter 224 by 224 by 3. Then we are setting the optimization parameter. So optimizer is equal to tf.keras.optimizers.legacy.addm. So we are using addm optimizer as we used in case of GIN, and we are setting the parameters of that to 0.0002 and 0.5. For much detail or in detail understanding, we can refer the Keras library for the optimizers. So we can go to the Keras and we can write down here optimizers in Keras. Fine, and we are using addm. So if we click on addm, it will show us the complete detail that what are the parameter values. Fine, the first one will be learning rate, beta 2 is equal to 0.99. So it takes many parameters while it learns. Fine, so if we do not set any parameter, then it will consider the default value. But if we write, see for example, learning rate, by default learning rate is 0.001. And in our code, we are setting it to 0.0002. And beta 1 is by default 0.9. We are setting it to 0.5. Fine, and based on this parameter, this optimizer will optimize the weights. Then there is a discriminator, VGG function, VGGNet, and then there is a generator. So ideal flow is generator followed by the discriminator, but code is just here and there. So first we'll understand the generator function. So like we created generator in last video, similarly here also we have to create the generator. But this generator is different than the actual or the original generator. So let us see how it is built. So when we go to build generator function, okay, so we have to press Ctrl and click on that generator, build generator function. So it comes here. So this is the definition of build generator, how it generates the generator. So there is a function called residual block. So residual block will add the residual blocks into the network. Now what is the use of residual block is? So for that I have some articles. I will share the link, you can refer it. Fine. So basically the task of residual block is, normally what happens, all layers are connected with next layer, something like this. See, this is how all deep neural network architecture looks. Convolution, then there may be pooling. So this is the one block, then again there will be convolution, then pooling or something like that. Fine. So this is the block 1, block 2, block 3, and different number of channels we might be creating. So and the image size will also change, and at the end for the classification we might be using the dense layer. So these connections are sequential. The first layer is connected with second is connected with third is connected with fourth, and so on. So sometimes what happens, if we have more number of layers, then model will have overfitting. That means it will learn the unnecessary features as well. Instead of focusing onto the prominent feature, if we have more layers into the network, it will start learning unnecessary things. So that is called overfitting, and due to overfitting, the accuracy will reduce. So it's not like that if we keep adding the layers, then more and more features will be extracted and model will become robust. No, it is not that. With one block, we may not be able to extract the sufficient feature. So we are going for second. So it will add another level of features. So we have now more features, fine-tuned features. So accuracy may be increased compared to one block. Then we are adding the third. So third will add another layer of features. So accuracy will increase compared to 1 and 2 block if we use 3 blocks. But if we keep adding such blocks, after some times there will be a saturation in learning. And it will be saturation in learning, and there would be then overfitting, and then accuracy will keep decreasing even if we keep adding the layers. So what residual block does, it will simply skip some of the connections. So instead of connecting first with second, it might connect first with third or first with fourth, something like that. So that kind of skip connections we can use. So this article is all about that. So it shows that whenever we are having a more saturated training, then there could be a lots of test error. And for that we have to add residual block. So residual block might connect our input directly to the output. You see that it is skipping the in between layers. One weight layer 1, weight layer 2. So instead of going sequentially, we can also directly skip some of the layer, and we can have a connection to the next to next or next to next to next layers. So by this we can avoid overfitting. So some of the ideas to avoid overfitting is, one of them is a residual block, and we can also use the dropout ratio. Somewhere we will be using that dropout ratio as well. Fine. So this is the residual block. So what it does, it will create one block. D is equal to convolution 2D. Number of filters we will be passing when we call it. See, here we are calling it residual block. We'll check it when we'll run the code. Then kernel size is 3, stride is 1, padding is same. That means whatever is the input size, same will be the output size. And whatever image is coming layer input, that we are passing here. Fine. So it will perform the convolution 2D. Then we are applying activation function relu on that D. And then we are calling the batch normalization to normalize the input. Fine. So that D is created. Again, on that D, we are applying convolution 2D with filters. Kernel size is now 3, stride is 1, padding is same, and then D. And D is equal to batch normalization with momentum. And then we are calling D is equal to add D and layer D. So what will happen? This generated D now will be connected with the layer input. So you see, we have one block here, then another block here. So the another block we are directly connecting with the layer input. So we have skipped this. So are you getting? What we are doing is, we have one input layer, then we have one block is this, then we have another block is this, and then we are directly connecting this second block with the layer input. That means first block, that is this, has been skipped. Right? So that is what residual block is doing. It is skipping some of the connections, and finally it will return that D. So remember that residual block is adding 2 blocks, and it is skipping one from the connection. Then we have a deconvolution 2D layer, deconvolution 2D function. So what it does, we are passing the input layer, then it is upsampling it. It will upsample is by size is equal to 2, and then it is performing convolution 2D with 256 filters. Kernel size is 3, so we are using 3 by 3 filter. Stride is 1, and padding is equal to same. Okay? And then we are applying activation relu on that, and that we are returning. So D stands for residual block, and U stands for the deconvolution 2D, that is the upsampled image. Fine. So from here all will start execution of the function. These both are function. Sorry. Here. These both are function. They need to be called. Fine. So when we are in build generator function, the actual call or the execution will start from this line. So image is equal to input dot self dot immune space shape. So immune space shape we have already initialized in constructor. One immune space shape, that is 224 by 224 by self dot channel, which is 3. So that is what we are putting it into the img variable. So img would be something like identical to what we saw earlier. Right? So I am writing these lines here. This is the line, and its size would be batch size by 224 by 224 by 3. Now I will write line by line code here, and I will be mentioning the size as well. Then we are calling C1 is equal to convolution 2D. Convolution 2D function we are calling. 64 filters we are passing. Kernel size is 9. Stride is 1. Padding is same. That means output size will not change. It will remain same. And we are passing the input image here. So convolution will be done on C1. And then we are applying the activation function relu on that C1. So see, when we do this, okay, the size will not change, only number of channels will become 64 because we are passing 64 filters here. Okay? Next, cross attention layer. Now here we are adding a cross attention layer which was not used in the normal GAN. So cross attention layer, you just press Ctrl and hover it on this, so it will be highlighted, then click it. Now what is the task of cross attention is, cross attention layer will calculate vertical and horizontal features from our image, and it will also find the intersection, or the we can say that's intersection of the features from both the channels. So again I will provide the articles on that what cross attention does. So this is the article which will describe what cross attention is having, what are the advantages of cross attention, right? So cross attention operates on two different input sequences, a source sequence and target sequence, and it is typically used with the decoder and so on. Fine. So when you will read it, you will realize that what cross attention is doing. So basically cross attention mechanism will focus on vertical and horizontal features, and it will calculate the communication between those features. So for that we are doing this initialization, then there is a build method. So in build method we are having a vertical attention weights function variable, and we are adding the weight. Okay, so these are the parameters, that input shape we are passing, then units 32 we have set, initializer, that is a Glorot uniform method we are initializing, trainable is equal to true, and here we are saying that we want to extract the vertical attention weights. Similarly, for second is the horizontal attention weight. So for that we are passing here horizontal attention weight. So both weights are calculated. Then this is the super method. So super method will call the build method automatically. So this is okay. Then we are having the call function. So inside call we are doing tensor dot, that is we are performing dot product of input and vertical attention weights that we are storing into D1, then tensor dot input and horizontal attention weight. So what we are doing is vertical attention weight we are multiplying with input, horizontal attention weights we are multiplying with input, and we are generating D underscore I and D underscore double I. So we have these two additional feature. Then we are calculating multiplication of both the features. So multiply DI and D double I. So what happens? We have independent feature DI, D double I. Then we are calculating relationship between them. So we are simply performing multiplication of them, and we are calculating maximum of them. Fine. So what we are doing is, instead of a plain feature, now we are taking the relation between them as well, and finally we are concatenating all four of them. So concatenate D1, that is DI, D double I, multiplication of that and maximum of that. Fine. And then we are simply reshaping it to 224 by 224 by 224. That is what it will be returning. Fine. So we got now mixed features. Come back to our discussion. Fine. So here we are getting this. So cross attention layer 1. Let me show this. Cross attention, I have written here that what is happening into the cross attention mechanism. So first we are calling the build method. Inside that we are calculating vertical attention weights and horizontal attention weight, and their size would be 64 by 32. Then we are calling the call method, and we are taking the dot product of input with the cross attention vertical attention weight. The size of channel would be now block size into 224 by 224 by 32. Same we are doing it for the horizontal attention. Size will not change. Multiplication maximum. In that case also size will not change. It will remain same. And finally the cross attention layer here, what we are calculating here, that size would be 224 by 224 by 64. The reason is that here we are reshaping it and then we are returning it. If you see that, here we are reshaping this concatenated output into 224 by 224 by 64, and that reshaped output has been returned. Fine. So here at this place, cross attention layer 1, the size would be 224 by 224 by 64. Next, R is equal to residual block. Now we are appending residual block to cross attention layer. So we have an input, then we have a cross attention layer, then we have a residual block. Fine. So residual block function, we already know that what it does. Fine. So it will create one block, then another block, and it will simply connect the input to the second block. So that's what this is doing. and the size of that block would also be same, 224 by 224 by 64. Fine. Next, for this is the for loop, so it will iterate 16 to 1. Okay, it will iterate 15 times, and every time it will be adding the one residual block. So 15 times it will add the residual block. See, I have written this, r is equal to this. Size is not going to change, only it will create 2 blocks, skip 1 and have a connection from first to third. Something like that, it will create 16 residual blocks in total. Next is C2 is equal to convolution 2D 64, kernel size 3D, stride 1, padding same, and R. So whatever residual block R was the last, that is given as an input for the convolution, and we are creating C2. So C2 will have the same size because we are not changing the number of filters, it is still 64. Then we have a batch normalization, and C2 is equal to add C2 C1, and we have added that. Then we are performing the upsampling. So U1 is equal to convolution 2D C2. So whatever C2 output was generated, that we are passing into deconv 2D, and we have already learned that deconvolution 2D is upsampling the input. Fine, and we are using here 256 channel. So if we look at this convolution deconv function, then you see that the original size was 224 by 224 by 64, but now we are keeping its size is equal to 2. So the channel size was, the image size was 224 by 224. It has now been 448 by 448. It has doubled because here we have used size is equal to 2. And then we are using 256 filter. So 256 channels will be created. So now the size of U1 would be 448 by 448 by 256. So we have performed upsampling. Then again we are performing the same on U1. So U1 size will also be doubled. So 448 by 448 will become 896 by 896. And number of channels are still same, 256. So that will remain 256 only. So this would be the image size at 896 by 896. And how many feature maps or the channels we will have? 256 channels will be there. Fine. After that, we are calling convolution 2D, and we are fixing the number of channels to 3. Kernel size is 9, stride is 2, padding is same, so image size will not change. Activation is equal to 10H, and U2 we are passing. See, always remember that whatever output we have generated in previous step will be given as an input to the next step every time. See, C2 is generated here, fine. So that C2, this is the adding, so we are simply adding C1 and C2. Then whatever C2 was generated here, it is given as an input to the next line, and we are generating output U1. That U1 has been used as an input, and U2 is generated. That U2 is used as an input to the next line, so that it will form the sequence of layers. Fine. So after doing this, we will get 3 channels. Fine. Stride is equal to 2. When stride is 2, it means you are skipping every second pixel. So you are applying your filter on first position, then third position, then fifth position, horizontally as well as vertically. So the size of output image would be half. Okay. It will reduce to 50%. So as you can see that number of channel is 3 because we have keep it here 3, and then stride is 2, and that is why the size of image was 896 by 896 will become 448 by 448. So we performed downsampled, and the activation function applied was 10H. Next, again we are calling the same function. Right? Whatever gen variable was created here, that we are passing here. Fine. And we are doing the same thing. Stride is equal to 2. So the size of this gen would be half than this one. So gen was 448 by 448 by 3. So now this line will generate the output of size 224 by 224 by 3. Okay. Then generative model is equal to model img comma gen. Right? So we are passing our image and this model, finally generated model, into the model function, and we have, okay, so model function will create the model out of that. This is the Python code, we don't need to touch this, but model will be created, and then we are storing into generator model, and then we are compiling it. Here we are taking the loss is equal to MSE, optimizer is equal to Adam, and matrix is equal to accuracy, and generator model has been written. So now this much part has been done. This line is over now. Okay? So this line does this much amount of work. It will call build generator method. Okay? So it will go, it will call build generator method. So it will come here. It is having a residual block function, it is having deconvolution block function, then it is creating the input space size, then calling convolution, activation, then it is also attaching a cross attention mechanism to that, then it will add 16 residual block, then it will add convolution block, then it will perform upsampling 2 times, then it is doing downsampling, and finally it is building the model, compiling it, and it is returning it. So one line here, this one will do that much amount of task. Now let us understand what discriminator does. Okay, so in discriminator we'll go here, build and compile the discriminator. So here we have a function called build discriminator. So when we click on this, it will take us to the definition of discriminator. So here also we have one D block. So what D block does? Convolution 2D, number of filters it will apply, kernel size is fixed 3, stride is equal to stride. Okay, so this stride parameter is coming from here. Fine. Filters are coming from here. How many number of filters we want to apply? Batch normalization is true, so it will perform batch normalization every time. Padding is equal to same, and whatever layer input is coming here, that is given as an input to this convolution function, and it will generate D. On that D, we are applying the leaky ReLU. Okay? Like ReLU, there is a function called leaky ReLU, and if batch normalization is true, then it will perform batch normalization with some momentum value 0.8. Otherwise, it will not perform any normalization. Simply, it will return the generated D. And that is the task of D block. Now see how it operates. So this is the function. It will not invoke until we call that. So initially, now execution will start from here. D0 is equal to input shape of self dot immune space. So we know that shape of immune space is 224 by 224 by 3. So size of D0 would be, now we are going to the discriminator part. Right? D0 is equal to input space this. So that would be batch size by 224 by 224 by 3. Next is D1 block. We are attaching another block to that. So D1 will be used now as an input. Fine. So we are calling the D block again, this same block. What we are doing is D0 is our input, which we have already created in previous line. 64 is number of channel. Batch normalization is false. So it will go here. Filters would be 64. Kernel size is 6, same. Stride is 1. And padding is equal to same. And whatever layer D0. Okay, D0 will be copied into layer because that is the first argument. So D0 will go to the layer input and that will be passed here. And it will generate that convolved D, apply leaky ReLU, batch normalization false. So don't apply batch normalization. Simply this D will be returned. So now we have a D1. Okay. So the size of D1 would be 224 by 224 by 64. The reason is that we have used 64 channels here. Okay. That is why. Then we are attaching another block. D2 is equal to D underscore block function has been called. So this will invoke with this argument. And what are the arguments? D1 we are passing as it is. Okay, whatever was the output in previous layer that we are passing here. Then 64 channel we are keeping as it is. Stride is equal to 2. Now see, stride is equal to 2. That means your size will reduce by half. Okay? So here the size was 224 by 224. It will become 112 by 112. Number of filters we are not changing. It was 64 here. Same we are keeping here. So channels are 64 still here. Next, D3 block. D block we are calling D2 as an input, which was generated as output in last channel. And then we are passing here 64 into 2. That is 128 channels we are passing. Filters we are passing 128 filters. So see, the image size will not change because we have not changed the strides. So it was previously 112 by 112. Here also 112 by 112. But now the number of filters are 128. So the channels here generated are 128. Next, we are simply adding the strides. Okay. The number of filters are same, 64 into 2, that is 128. But stride is 2. That means whatever was the size in previous layer will be reduced by 50%. So earlier it was 112 by 112. It will become 56 by 56. Fine. And number of channels, see, it was 128 here. We are not changing, so it will remain 128. In next line, again, D block, we are adding a new D block. And what we are doing is number of filters we are passing, that is 64 into 4, that is 256. Right? We are passing 256 filters here. So now number of filters will be 256. Stride we are not changing, so by default it will be 1. So when stride is 1, whatever was the input shape, same would be the output shape. In next layer, we are simply changing the number of strides. We are not changing number of filters. So filters will remain. Filters will remain same, 256. But stride is 2, so size of image has reduced to half, 28 rows, 28 columns. Next, we are adding 512 channels. So here you see that number of channels are 512. But we are not changing the stride, it is by default 1. We have already set it here that if we are not passing, then by default it will take 1. So shape will remain as it is, that is 28 by 28. Next, we are adding stride of 2. Filters we are not changing, so filter will remain 512, but the size will become now 14 into 14, okay, instead of 28 by 28. Next, whatever D8 we have, that will be flattened now. Flatten means till now it was a 2-dimensional array, 14 into 14. That was the number of rows, number of channels, and we had such 512 different channels. So flatten will arrange everything into single column. So what happens now, instead of this we will have 14 into 14 into 512. This would be the size of vector. So that is 1,352. So that is shown here. So what happens in flattening? Let me just show you if I can find flatten. Flatten layer. See, this is what happened. If we have a one image of size 3 by 3, then flatten will simply arrange it into the columns. So 110 will be stored here, then 422 will be here, then 021 will be here. So we have such, so what is the size of our kernel right now? That is 14 by 14. So instead of 3 by 3, we have 14 by 14. So that much long vector it will create. And we have such 512 vectors. So again such 512 vectors will be attached to that column. So it will form single column. So the size of single column would be 14 into 512. That is 1,352. Clear? Finally, we are having validity is equal to dense 1 and activation sigmoid and D9. So discriminator will return us only one value. There will be only one neuron now. Okay, and activation function is sigmoid. So this will tell us the class of the image. What is the class of the image? So that will be just a one number. So size of validity would be now batch size by 1. So if I have 100 image, then validity would be 100 by 1. Okay, and each value will tell me that what is the predicted class. Okay, what is the class of the input image. So class is just a one number. So if I have 100 image, I will have 100 numbers. And that is why this would be 100 by 1 vector. Okay. And then we are calling the model function, okay, where we are passing the D0, that is our input layer, and validity, that means the output or the labeled class. That is what we are doing here. Fine. So this much code will execute while we call this build discriminator function. So discriminator function, then we are compiling it with MSE optimizer is equal to whatever optimizer we have preset, and matrix is equal to accuracy, just like identical to generator function. And then we are using, see, this is also a new thing which was not used in normal GIN. We are also using VGGNet. So VGG is very popular deep learning model. I don't know if you know or not. So what it does, see, we use a pre-trained VGG19 model to extract image features from the high resolution images and the generated high resolution images and minimize the MSE between them. So what VGG tries to do, we will have original high resolution image and generated high resolution image, and it will try to extract the features in such a way so that the mean squared error between these two images will be minimum. That means the generated image should be or would be very close to the actual one. So that is what this VGG is doing. So let us try to understand what is happening. So again there is a call vgg.vgg self.vgg is equal to self.buildVGG. So again this is a function like a build generator, build discriminator, and we have build VGG. So when I press Control and I hover it on this, it will show me blue line. If I click it here, it will take me to the definition of VGGNet. So here VGG19 is an inbuilt function of Keras library. It will generate VGG19 model. So in VGG19 there are 19 layers, and that is why it is called VGG19. There is another variant of VGG is that is called VGG 16. In that there are 16 layers. Okay? So right now we are using VGG 19. Weights it is fetching from the ImageNet. So it is a predefined weights. Include top is equal to false. Input shape that is 224 by 224 by 3. That also we already know. Then what we are doing is set output to outputs of last conversion layer in block 3. So VGG layer is having many layers. So from the block 5 underscore pool layer, we are fetching the output. Okay? So we are not using the entire VGG architecture. From block 5, whatever is the output that we are fetching, and then we are calling the model function. So what it does, input is equal to VGG.inputs. Fine. So this what we are passing here, and output is equal to block 3 convolution 3 output. So that is what we are generating here. So it would be difficult perhaps to understand this because you don't know the architecture of VGGNet. But what it does, it will simply fetch the output from the 5th layer instead of going up to the end. And that output we are using right now here. And it will return the VGG model. Okay? So that comes here. So that much task is done by calling this function. Trainable is equal to false. VGGNet is already trained on 1000 classes. We don't need to retrain it. Otherwise it might take days to compile, train. Then we are compiling the model with the same parameter MSE, the optimizer we already set it here, and the accuracy. Fine. So generator is already, this we have already discussed at the beginning, generator is called. Then what we are doing is, see, image underscore HR, that is high resolution image underscore LR, that is low resolution image. Now high resolution image we are generating from immune space, and low resolution image we are calling it to the image space. So immune space, that means the images which are projected using LCPCN network, and image shape, that means this is the image which are augmented image without noise. Next, what we are doing is, now see, this is the sequence. This will, so up till now we have only created the networks. Now it will actually perform the generation. So generate high resolution version from low resolution. So we know that whatever original image we have, it is a low resolution image. Okay, we will call it as a LR. Now we are passing it to the generator function. Okay, so low resolution image LR, we are giving it to the generator. So generator will generate the FAC images. Okay? Generator will generate the FAC image. So generator is where we were. Generator, yeah. Generator will generate the high resolution image from this. Then we are extracting the features from the generated image. Okay? So this is the FAC image. It is not actual one because actual image is this image, low resolution image. From that we are generating high resolution image. We will call it as a FAC image. Then from FAC image we will call VGG model, and we will pass it FAC image, and it will generate the FAC features. So what we are doing right now is we are extracting the image features from the generated high resolution image. So that FAC image we are passing, and we are calling the VGG, and we know that what VGG does, it simply extract the features such that the mean squared error between the FAC image and the original image should be minimum. Right? Such kind of FAC features it is generating. Then what we are doing is discriminator.trainable is equal to false. We don't need to train the discriminator. Validity is equal to self.discriminator fake. Now we are determining that what is the class of this fake image. Okay, so that is the validity. So discriminator determines the validity of the generated high resolution image. Okay, so this image class we already have in validity. Now what we are doing is we are combining the model. So it will pass low resolution image, high resolution image, validity, and the fake features. These 4 parameters we are passing, and then we are compiling the model. So here we have a loss is, our loss is binary cross entropy loss, that is for classification, and MSE, that is for the generated images. See, we have this image and this image. Validity is the class, and these are the features. So based on features we have to classify the image. So for classification, the loss, binary cross entropy loss is used, and to minimize the difference between 2 images, we have a mean squared error. So mean squared error is typically used to compare 2 images, how similar or how different those images are. And loss weights we are assigning to 1e minus 3 and 1, and optimizer is the default one. So this is what the model will be created finally. Okay? and that will tell us everything. So that is what this stack attention GAN is. Right? And this is what all the dimensions and everything I have mentioned into this file. This file I have already sent you. Right? So here it is a yellow, that is a generative adversarial network we learned in the last video. So it is having generator and discriminator like this. Then we have a Sargan. So in that case, generator is having a cross attention layer, and then we have so many 16 residual blocks. Fine. And it is also generating a high resolution, low resolution from the VGG net. So VGG 19 we have used, and this is the architecture of the discriminator. So this is the difference between both of them. You see that their architectures are quite different now, and that is why the proposed model is generating the better images. So with that, I am stopping here. So this particular line of code, Sargan, where it is, yeah, this line of code has been over now. Right? We are done with this. Okay, so let's stop here. It's my office time, so I'll now leave for the office. Thank you.